We're going to get started by talking about superposition laws. Now, superposition is a mathematical property and a technique that you can use to solve problems. And what it means is that the solutions of a problem can be added together. And that sum of solutions is also a solution. That is a property of linear differential equations and their solutions, which happens to govern most of electromagnetics. It depends on the material that you are existing in, but that's not something that we're going to worry about until a later chapter. So chapter 2 of our book is about superposition laws, which are Coulomb's law and the Biot-Savart law. They're grouped because they have similar mathematical forms. Coulomb's law refers to the electric field, and the Biot-Savart law refers to the magnetic field. Today we're going to talk about Coulomb's law stuff, starting with electric charge. What is it? Charge is a property that particles have. There are two kinds. And we refer to them as positive and negative. They have units of coulombs, which uses the symbol capital C and just measures how much charge there is. And they have the property that, unlike charges, meaning ones that have different signs, attract each other. They exert forces on each other that cause them to move together. And like charges, repel. In this class, we're going to talk about point charges a lot. And what we mean by a point charge is that it is an object that has charge, might represent a particle or something, that has approximately 0 size physically. We often use the word infinitesimal for that, which means so small that its physical size doesn't matter, and it has charge. Those are the two properties of a point charge. Most of the time we use the symbol Q to represent a point charge. Sometimes we use the symbol little q also. Both of those things can mean a point charge. Now, we said that charges exert forces on each other. Coulomb's law describes, it tells you how much force and in what direction do charges exert forces on each other. Coulomb's law tells you that the force, if you have two charges, let's say one of them is called Q1 and one of them is called Q2, and these are both point charges, the force on Q2 due to charge 1, which we write as F21, is going to be equal to Q1 times Q2, those are the amounts of charge, divided by 4 pi epsilon naught, which I'll tell you about in a second, r squared times a unit vector, a hat r12. So let's take a look at the different parts of these equations. Q1 and Q2 are the charge amounts with sign. So they might be plus or minus. They might be positive or negative amounts of charge. Big R is the distance between Q1 and Q2. And that unit vector, a hat r12, is the unit vector pointing from Q1 to Q2. And last thing, epsilon naught, that's a little subscript 0, but in electrical engineering we usually pronounce that naught, N-A-U-G-H-T. And that's kind of because of the English language roots of electrical engineering. Naught is a common thing in British English to call the number 0, and that has propagated over to America for some reason. Epsilon, Greek letter epsilon, epsilon naught represents a physical constant, which is the permittivity of free space. We'll talk in a later chapter about what permittivity actually is, but free space is just another word for empty vacuum. And the value of epsilon naught is approximately 8.854 times 10 to the minus 12th farads per meter. So we've broken down all the parts of this equation. Let's draw some diagrams to show you how these things play out. Now, if Q1 and Q2 are both positive or both negative, the situation is going to look like this. Here's Q1, here's Q2. The unit vector from Q1 to Q2 points in that direction, so that's a r12, like in the equation. And the force that Q2 experiences is going to be Q1, Q2, a hat r12 over some constants, 4 pi epsilon naught times the square of the distance. So F21 might look like that. If Q1 and Q2 have different signs, we'll draw that situation. Q1 is over here, Q2 is over here. The unit vector still points in the same direction, AR12, but the direction of F21 flips, and now it points that way, because the sign of this Q1, Q2 product is now negative. In the scenario above, if Q1, Q2 is positive, then F21 has the same direction. I'm just going to write down parallel to a hat R12. Actually, parallel is a little bit wrong because you can kind of be parallel. Anyway. Obviously, there is also a force on Q1 at the same time as this force on Q2 is existing. So if you have the same sign, there's Q1, there's Q2, A hat R21 looks like that. And if these two have the same sign, then the force on Q1 is going to point in the same direction as that unit vector. So that will be F12, like that. And if they have different signs, you got Q1 here, Q2 there. Unit vector still points from Q2 to Q1. But the force that Q1 experiences pulls it towards Q2.